we have one simplified differential equation, but it's still very difficult to get analytic solutions unless we make further assumptions. Okay? Here, we make the first assumption, the fast spectrum absorber. Okay? So what does this mean? Let's take a look at this figure. Say initially you have a lot of electrons on ground state, level 1. If you have a short pulse come in, the pulse duration is delta t, pulse width is delta t. What would happen? Okay. You must have absorption because ground state electrons interact with incoming photon due to the input pulse. So you will excite some ground state electrons to level 2. Then, if the material belongs to fast spectrum absorber, it means not only the two relaxations are fast, but also the relaxation between level 3 and 4 is also very fast. Okay? So you have 3 fast relaxation processes. In that way, you can imagine the electron on level 2 will be quickly dumped to level 1 by way of levels 3 and 4, of course. Okay? But this is true only if this condition is satisfied. Your lifetime constant, tau A, is much shorter than your pulse width. The pulse width delta t. If this is true, you can make this picture. Okay? So simply speaking, an excited electron returns to level 1 immediately. Okay? So we can review the differential equation we got. This is the original equation. If this picture is true, we can roughly mention that the time derivative of n1 is almost 0 because it's nearly a constant. Okay? If this is 0, then you can easily solve this differential equation. The solution is something like this. Na is the total number density over 1 plus number, which is always positive. Okay? The number is the power P of t, depending on your pulse shape, over the saturation power of your material. Okay? So this is a number. 1 plus a positive number, that means your N1 is always less than, at best, equal to Na, which is true, right? You can never, N1 can never surpass the total number density. And if you borrow the definition we introduced before, the loss coefficient is related to N1 by this simple relation multiplied with VA over constant 2, then you can write down the dynamic loss coefficient L as a function of t is equal to this. The denominator is the same. You only have to replace the numerator from Na to L0. L0 is the small signal loss. Okay? The loss when there is no light. The loss is the biggest because of no saturation. Okay? So this is what we have. The solution to the differential equation under the condition fast spectrum absorber. Okay? But I believe a formula like this is less impressive. So let's take a look at the illustration. Imagine you have an input laser pulse. The power as a function of time is represented by the red curve. Okay? And by using the formula we just obtained, the loss coefficient is equal to small signal loss over 1 plus P of t. P of t is your red curve over P sub A, the saturation power constant. You got the blue curve. Your loss curve is represented by the blue curve. There are a couple of parameters like L0. the small signal loss, you can easily identify the meaning of L0, right? When the loss is L0. When your power is 0, here and here, your loss is maximized, your small signal loss. Okay? From here, you can identify when can you have the biggest loss. When all the electrons stay on level 1, so level 1, N1 is equal to total number density Na. At that moment, you have the biggest loss. Okay. PA, by definition, is like this. And its meaning can be figured out by looking at this term, P of T over P sub A. So it means when your power is big or at least equal to P sub A, this term is larger than or equal to 1. Okay? If the ratio is too small, P of T is much less than PA, this term is very unimportant, right? So your loss is roughly small signal loss, L0. So you can easily identify the meaning of PA is the criteria above which your loss saturation matters, below which there is loss saturation but very unimportant. You can hardly tell. Okay? And the L minima means the minimal loss you can have. It occurs when your pulse has its peak value, right? Because when your P of T is maximized as peak power, this term is biggest, so you have the smallest loss. Okay. So anyway, the dynamic loss can respond to the laser power immediately. So roughly speaking, the shape of the pulse, the red curve, can be not exactly, but quickly manifested in your dynamic loss curve, the blue curve. So whenever your pulse shape has some small change, you can tell from the blue curve. Okay. And the second thing is saturation is evident when your peak power is greater than or equal to PA. If that is not the case, you will have a very flat loss curve. Okay? The blue curve is almost flat. You cannot see any saturation. Okay? So simply speaking, if your laser is not strong enough, loss dynamics is unimportant. So it only matters when you have a strong short pulse. Otherwise, this dynamics is very unimportant. Okay, the second case is the other extreme, the slow satural absorber. But the mathematics is a little bit more complicated. So we cannot get a solution for the equation, a single solution for the equation, differential equation. We have to get different solutions at different time frames. So this is the stage 1. Stage 1 means when your time, observation time, is smaller than T prime. By this figure, you can tell. T prime means the trailing edge of your pulse, 就是整个脉冲的尾巴。在这个之前都叫做 stage 1. At stage 1, we can try to get a single solution. But this solution does not apply for stage 2 after T prime. Okay, that's the point. We have no choice because if you do not divide into 2 stages, you cannot have analytic solutions. Okay, so if it's stage 1, what happens? Again, you have an input pulse. There is absorption, but now the material is slow satural absorber, so that means the relaxation from level 2 to 3 is fast. But from here to here is slow. So you cannot copy the picture we used before. What happens in this case is like this. If your pulse energy is strong enough, then it will not only excite a single electron to higher level, but more electrons. Okay? No relaxation between levels 3 and 4, and more electrons will be excited from ground state to level 2, then quickly down to level 3. A lot of electrons will stay here. Okay. Okay, so let's go back to the differential equation. Okay. There are two terms on the right-hand side of equality. The first one is about absorption, because P of t, input power, it's about absorption. The second term is about relaxation from here to here. Okay? And by this figure, you can tell in stage 1, there is no relaxation, right? Because it's very slow, no contribution from relaxation to level 1. So you can eliminate the second term to 0. And this is your simplified differential equation, where we introduce another parameter, U sub A, which is saturation power times lifetime constant. It's a quantity about energy. So it's defined as absorption saturation energy, not saturation power, but saturation energy. Okay, then how to get the analytic solution? This is the simplified differential equation. Can you solve it analytically? It's not that difficult. You can just rearrange, okay? NA to here, dt to here, okay? Then integrate for both sides of equality, okay? What is the integration of this one? It's a natural logarithm function, right? You have studied it in calculus. What's the integration of this one? Power after time integration means energy, right? So you have a numerator, U of t in the numerator. It is the pulse energy. U sub A is a constant, so you do not have to integrate it. So you have this one. Then what is the solution to N1 as a function of time? If log N1 equals this one, what is N1? It's by definition of logarithm. E to the this one equals N1. Okay, so that's all we need. Okay, but you know, to get an exact solution for a differential equation, you still need initial condition. Especially this is a first order differential equation, so you need one initial condition. This is our initial condition. We assume well before the coming of the input pulse, the number density of N1 is some given number, N1 super I. Super I means initial. So this is your initial number density. Okay, this is some physical quantity you need to know beforehand. With this initial condition, you can write down the analytic solution of N1, which is this initial number density times exponential decay function, where the exponent is a number, a constant number, U of t over U of A, where U of t is defined here. Time integration of your power. Okay, so by using this figure, you can quickly identify what is U of t. Cumulative pulse energy up to observation time t. Integration from minus infinity all the way to the observation time. And the area means the cumulative energy up to the observation. Okay. So basically, your number density is is dependent on the cumulative energy, normalized to saturation energy. The bigger the ratio, the stronger the saturation. Okay? But actually, we wonder the dynamic loss, right? L of t equals N1 of t, which is solved here, times effective volume VA over constant 2. So this is the solution. Initial number density is replaced by initial loss coefficient. Okay? But be careful, L super I is the initial loss. It's not equal to the small signal loss, L0, we have seen in the previous example. Okay, so what does this mean? It means even your pulse does not come, your loss can still be smaller than the small signal loss. Okay, we will see this a little bit later. Okay, but anyway, this is not L0. This is dependent on the initial number density, your initial loss. Okay, let's take a look at the figure. The red curve is still the input pulse, the instantaneous power as a function of time. The blue curve represents your dynamic loss. But you have seen a very different shape compared with fast saturable absorber, right? What is the shape in the case of fast saturable absorber? The blue curve will decay, then grow up again, right? But here, it's monotonically decreasing. There is no recovery within stage 1 before T prime. There is no recovery. The blue curve just keeps on decreasing. Okay. So what happens? The dynamic loss cannot respond to the fast envelope of the laser pulse, the red curve. It's too slow. It cannot trace or it cannot respond to the red curve. It only responds to its cumulative energy, which means the yellow shaded region. Okay? So it means as long as area is the same, no matter what's the exact shape of the blue curve, there is no difference from your blue curve. You cannot tell because its response speed is too slow compared with your pulse width. Okay? So that's one thing. You can also justify this behavior by the formula, right? You can see now the pulse parameter is cumulative pulse energy, U of t, the area function. It's not the envelope power, okay? It's not the exact pulse shape. It's only the area matters. Okay? So that's why even after your pulse peak, right, your instantaneous power decreases, but your area keeps on increasing. Then your exponent is increasing. It's a minus sign and in the exponent, so your blue curve keeps on decreasing. Okay, so it's a very different behavior. Second observation is the saturation is evident when your total pulse energy, what is your total pulse energy? The total area under the red curve. If the total area is bigger than the saturation energy, then this term matters. You can see a clear loss saturation. On the other hand, if your pulse energy is too small, this ratio is very small, then the blue curve is close to a flat curve. You cannot observe the loss saturation. Okay, any question?
它如果那个就是它给进的脉冲量太高，它的整块晶体就会锁在一个就是 loss 就才能提的状态，这样。
你可以 repeat 一下你的问题吗？
你现在是脉冲光，你现在丢进去的那个脉冲太快，
嗯哼。
然后所以你的那个晶体它反应，它现在 loss 就会掉的比原来要多。
哦，没有，掉的大小不一定，这是比掉的快慢而已。就是说这个 material 作为一个 absorber， 它的 respond speed 来跟你的 pulse duration 来比，如果慢很多就会遇到这个情形，如果快很多就会看到上一个情形。至于它们掉下来的程度，程度大致上是讲这一段嘛，这一段有多深，那不一定，这个 case 不一定掉的比较深哦。这个 case 会掉多少是看这个 minimal loss 跟 initial loss 之间的 difference。clearly 它是由这个决定的 ，total energy over saturation energy 放在指数里，这个数字大小会决定它掉多深。而刚刚那个它不看 energy， 它看 power，right？ So you can see the saturation depth, the distance here, depends on what? Depends on peak power over saturation power. The bigger the ratio, the stronger the saturation. Okay.
我的意思是说，你的脉冲这样这么短，脉冲打进去，或者你的 loss 就锁在 minima
第二个 case 吗？
对。
是啊，最多掉到 L minimum。Here. The smallest loss coefficient you can have is dependent on the total pulse energy. Okay? 你已经把你整个面积都用上去了，你的 energy 已经不可能比它还大了嘛，对不对？所以是 total pulse energy 决定你的 saturation 有多严重，而 fast satural absorber 是 peak power 决定你的 saturation 有多严重，这两个不一样。
所以它的 minima 是在过了一个就是一个 lifetime 以后，它就会降回去。
OK， 我们接下来就要看 Stage 2。我们现在只 solve Stage 1， 我们还没看到后面，不可能停在这里，对不对？一定要有后续的这个演变，对不对 ？This is only Stage 1. So what's Stage 2? Stage 2 means after the pulse tail from T way to infinity. Okay. Then what happens? This is the figure about the end of stage 1. So you still remember the input pulse excite a lot of electrons to level 2, then quickly dump to level 3, but stay here because relaxation is too slow. So in stage 1, we assume there is almost no relaxation. So all the electrons, excited electrons, stay on level 3. But then in stage 2, remember here, there is no input photon anymore, right? The pulse passes through. There is no pulse. So there is no further absorption here. Then the slow relaxation takes over, right? So what happens? Although it's slow, but gradually electrons dump to level 4, then quickly dump to level 1, and the process continues. So eventually, all the excited electrons will relax to ground state, level 1. Okay. Then how do we modify the differential equation? This time we have to eliminate the first term, because now P of t is almost 0. There is no pulse in stage 2, right? So this is the simplified differential equation in stage 2. And it's not difficult. You can solve. The solution is something like this, exponential function. And if you consider the loss coefficient, it's like this. where D is some unknown coefficient you have to solve by initial condition, right? Again. What is our initial condition? Initial condition of stage 2 actually is the end condition of stage 1 because they are connected with each other, right? So what happens by the end of stage 1? In stage 1, we know the last moment is t equals t prime, right? And at that moment, your loss is this one, loss. And the minimum loss depends on the total pulse energy saturation. So this is your initial condition for stage 2. You can write down the solution to stage 2. Okay? The formula is not important, but basically the loss recovers from the minimal loss way to trying to recover to small signal loss before the next pulse comes in. Okay. And the speed of the recovery depends on your tau A, right? Your lifetime constant of the material.